Okay, chapter 17, part 3. In this part, we're going to talk about other aromatic compounds that either have charges or heteroatoms. And so we're going to start off with aromaticity and ions. So if we look at cyclopentadiene, right, this is non-aromatic. Rule 1 is not fulfilled. This is a CH2, and you can't hold that flat, right? There's not a p orbital so that you have a fully conjugated ring. However, what about if we consider the cyclopentadienyl anion and the cyclopentadienyl cation? Well, first of all, let's start here. This is aromatic, and I want to explain why. You would expect this to be more stable because of the resonance, but this winds up being more stable than resonance can even explain. And if you look at the pKa values, you can start to understand a CH, especially an sp3CH, is not acidic. If you look at the pKa of something like ethane, your value is going to be upwards of like 50. But here, you can actually pluck that proton right off, and it's not just because of resonance. It's attributed to aromatic stability. So let's think about what this structure looks like. And to do that, we really need to think about the carbanion. Now in Gen Chem, you were taught to treat sigma bonds and lone pairs as the same thing when you were figuring out hybridization. And that's not untrue. But, first, the reason that occurs, the reason why normally you would say this is sp3 and tetrahedral geometry is because that allows the bonds and the electrons to spread out as much as possible, which is typically more stable. But a lone pair will accept being pushed closer together if it helps it achieve aromaticity. So this is actually sp2 if it's held planar, right? So if I say assume planarity, both of these can be planar. Now, this one cannot, because there's not a lone pair there. Those bonds are not going to be able to be squished together so that it can be planar. This one will always have that tetrahedral geometry on that carbon. But the charge, the fact that we are not bonded to another nucleus, gives us a little flexibility. Now, if it's held planar, that means we have sp2 hybridization around that carbon, and it's trigonal planar. And then we have a lone pair that will be in the p orbital. This is a mess what I just drew, but that's okay. Okay, we don't have a picture of it, but what that allows for is in the double bonds, you have your p orbital. You know this because they're pi bonds. And now, since we have a carbanion, and we can make it sp2, there is going to be that p orbital left over, and that's where the lone pair is going to be, right? So the lone pair goes in the p orbital. So now, when we check the rules, there are 6 electrons, or 3 pairs in that pi cloud. 1, 2, and then 3. It's an odd number of pairs, and it satisfies rule 1, so it is aromatic. You also can see, if you make the little frost circle, for the cyclopentadienyl ion. Right, if that lone pair is pushed up into the pi cloud and you have 6 electrons, you have 1, 2, 3, 4, 5, and 6. Now you get that nice paired up electron system. This is aromatic. Now, it's a little bit easier to see how rule 1 works if you have a plus charge. Because if you have a plus charge, that carbon has 1 hydrogen, 1 bond to one side of the ring, 1 bond to the other side. So only 3 bonds, it's also sp2 hybridized. And there is an empty p orbital. So rule 1 is checked, right? This can be planar, but there are only 2 pairs of electrons, right, of pi electrons. And so even though this is fully conjugated, right here you have an empty p orbital that allows that, but you have an odd number. So the cyclopentadienyl cation is actually, if it's planar, is anti-aromatic. And if you look at, and we'll go to the frost circle here, the frost circle, if there's only 4 electrons, you're going to have 1, 2, 3, and 4, right? So still an odd number, much more likely to be seen with anti-aromatic. We can do something similar here with the cyclotetraheptenyl ion. Right, so for one, I'm so sorry, drawing 7-membered rings is no fun. You won't have to do it for a grade if that's any consolation. Of course, the neutral molecule would be non-aromatic because of the CH2 up top. But let's look at the anions and cations. Let's start with the cation here. With the cation, rule 1 is satisfied and so is rule 2. Because it's a carbocation, you know it can be flat with an empty p orbital. And then you've got 1, 2, 3 pi bonds. So that's an odd number. You have a fully conjugated ring. Hugel's rule is satisfied. If this is planar, it's aromatic, so it's probably going to be planar. That is just hexane. Here we go. Let's draw the other option. What if we deprotonated it and had a negative charge? Well, if your carbon is held planar here, if this carbanion is held planar, well, then 1 is satisfied because you'll have an unhybridized p orbital that has a lone pair in it sticking up. And then you have 1, 2, 3 double bonds. Right, and each one of those is going to have a p orbital that goes up into the sort of pi cloud. Right, so 1 is satisfied, but 2 fails, right? Because you have 1, 2, 3 pairs from the double bond, and you have another pair from the carbanion. So if this one is planar, it would be anti-aromatic. And you can see that here. If you've got 6 pi electrons, right, that's 3 pairs, versus 4 pairs and 8 pi electrons, right? So if you go 1, 2, 3, 4, 5, and 6, that gives you that aromatic plus charge. If you 1, 2, 3, 4, 5, 6, 7, 8, that represents the carbanion. You have high energy, unpaired electrons. It's not stable. You also have resonance, of course, with these. Now, so what you want to keep in mind before we move on to nitrogen, for carbon, if there is 3 bonds and a plus charge, or 3 bonds and a lone pair and a minus charge, Both can be planar. And when you are counting electron pairs, you must count the electron pairs in a carbanion. In a negatively charged ion with carbon. All right, so that's your rule for carbon ions. Now, let's talk about heteroatoms. Heteroatoms are essentially not carbon or hydrogen. So when we look at pyridine and pyrrole, what's interesting about these two is even though they look different, there's some significant differences here in the bonding. They're both aromatic. So let's think about that for a moment. Might be easier to understand why pyridine is aromatic because it looks so much like benzene, but you want to be careful about nitrogen. Nitrogen's another one of these where in Gen Chem you would have learned that this is sp3 hybridized, but just like the carbanion, this can be planar. All right, it can be sp2 hybridized with a lone pair in that p orbital. Or, well, let's say not with the lone pair. It can have a p orbital if you flatten it. Because it's not 4 sigma bonds, you can do that here. Now, in pyridine, this is sp2 hybridized anyway because you have that double bond. So, where is this lone pair? Sorry, and that lone pair will, no. Okay. So we have to think about what's going on with this nitrogen. In this case, if it's sp2 hybridized, what is in these 3 equal energy sp2 hybrid orbitals? Well, one of them's going to carbon, one of them's going to carbon, the other one has your lone pair. So this lone pair is sticking out of the ring. All right? Which means that there is an empty p orbital. Let's make a note there. Empty p orbital. And then you've got 3 lone pairs from the double bonds. And so rule 1 is checked because you have that empty orbital from the nitrogen. Rule 2 is checked because you have an odd number of pairs. And it's aromatic. The main thing that you have to get over, and this is more of an issue with pyrrole, is the fact that the hybridization you learned in Gen Chem is a little bit more nuanced. All right, this nitrogen here has a lone pair, but in this case, you don't have a double bond, so you don't have a pi bond already giving you that p orbital. So if we make it sp2, it can be planar, but the lone pair goes in the ring, right? Or above, goes in the pi cloud. All right, so there's like a p orbital here. That's where your lone pairs are. And then, of course, there's p orbitals on each carbon of the double bond. So rule 1 is checked. Now the lone pair of the nitrogen gets counted. So we have 3 pairs. So that is also checked. This is also aromatic. When you look at the orbital diagrams here, you can see that the nitrogen and the pyridine, that lone pair sticking out away, versus in the pyrrole, it's up here in that cloud. You can also see this evidenced when you think about the basicity. Nitrogen with a lone pair is a base, right? A weak base, but a base. If that lone pair is tied up in the aromaticity, it's not going to be nearly as basic. All right, here pyridine acts as a great base, but pyrrole, not so much. The starting materials are favored. Why is that? Well, when we compare the two, you can take this and make a bond, and you still have an aromatic product. However, if the lone pair was what was making it aromatic, and you take that away, then you're making something non-aromatic. Aromaticity is always desirable. So to say that this one is more acidic, more basic, has everything to do with the fact that the product will maintain aromaticity. You can even see it here in the electrostatic potential maps. On the pyridine, that lone pair is isolated on the nitrogen or localized on the nitrogen, whereas on the pyrrole, that lone pair is localized over or delocalized over the whole molecule. Polycyclic aromatic compounds, you're just going to be using the same rules, right? As long as it's fully conjugated all the way around, rule 1 is good. And then count up the pairs. 1, 2, 3, 4, 5. That would be aromatic. 1, 2, 3, 4, 5, 6, 7. That would be aromatic. It's another 7, right? All 3 of these are aromatic. We're not going to worry anything beyond that. In the last video, we will talk about a reaction or two at the benzylic position.